We are on a new section, and we're on to chapter 6. And if you wonder what happened to chapter 5, I didn't miss it. We were never going to do chapter 5. It was using what's called the binomial distribution, which isn't part of our course. But what is part of our course is the normal distribution, and it has lots of names. Imagine that you have some data and it looks like this, so the population, there's some very short people, there's a lot of people round about the middle, right, and a few very large people. When you see this shape to your data, right, so this is everybody in the population, that's my age, that's your age, whatever it is. This is a very, very common distribution. It's got lots of names. It's called the normal distribution, the general normal curve, the general normal distribution. It's called bell-shaped. It's called mound-shaped. And I bet you I've forgotten a couple other names. But they're all that guy, right? They're just different names for the same guy. So it is what it is. Now, what they've discovered through experience, right, there's no theory behind it, is that in many, many cases, when you get this nice symmetric shape, that the top of the hill, right, the place where most people have their age or their weight, that will be the mean of the entire population. Does that make sense that the middle would be the mean, right? And then they also noticed that the standard deviation was important, because if you take the mean and you add 1, then 2, then 3 standard deviations, you get to here. And if you take the mean and take away 1 standard deviation, 2 standard deviations, and finally 3, you get to here. And almost all data that we've collected, almost all of them, if you go 3 standard deviations from here to here, you get virtually everybody. The only people that are left are the outliers. And that's quite interesting that we get that. So let's get used to some symbols. You've seen this guy before. I've kind of emphasized the line. It's the population mean, and you pronounce it as mu. And the population standard deviation uses that funny little guy with a little leg, and we call him sigma. Now, here's an example of a normal distribution. The mean is 20, and the standard deviation is 4. That's all they told me. It was normal in shape, the mean was 20, and the standard deviation is 4. Then I can actually build what the data would look like, right? Add and subtract 4, add and subtract another 4, add and subtract another 4. So if I put a little wall at 32 and a little wall at 8, there's very, very few people less than 8 and very, very few people bigger than 32. If you find anyone in that range, right, anybody bigger than 32 or anybody in this particular case less than 8, they would be considered an outlier. Remember the Bill Gates of the world, right? Really extreme values. And that's interesting that every set of data that we've came across, with minor exceptions, follows this pattern. That if you take the mean and only do 3 standard deviations away from it, that's pretty much everybody in the entire population, with a few outliers missing. Cool. Now, let's show you some homework questions where they kind of take that idea and they ask you questions. So here is a normal distribution, and 85, 87, 89, and 91. If they said to me, what is the mean? Looking at that picture, what number is the mean? Should be pretty straightforward. What number is that mean?
85.
85. Now, 85 to 87 to 89 to 91. Isn't the distance from here to here 1 standard deviation, which in this case would be 2? Are you comfortable with how I could tell the standard deviation just by looking at the mean and how far to the next number, right? There's 1, 2, 3 of them. Each one is a standard deviation. So from 85 to 87 is a standard deviation, 87 to 89. Now, what number is sigma mu plus sigma. What number would that be? What's that number? It's not a trick question. What would it be? The mean plus 1 standard deviation. What would that get you?
Would be 87.
Yeah. Simple as that. Suppose it said sigma plus, keep saying sigma first. Suppose it was mu plus 2 sigmas. Wouldn't you say 89? If it had said mu plus 3 sigmas, wouldn't you say 91? In fact, if they filled the numbers that would go this way, wouldn't this one be 83, 81, and then 79, right? If you went the other way. Right, here are two different looking, but both of them are normal distributions. Which one of those has got the larger standard deviation? Again, it's not a trick question. A or B, which one has the bigger standard deviation? Just by looking at it, you should be able to tell. Which one?
Would it be B because it's taller?
Standard deviation is how spread out the data is. So it's not how tall it is, it's the opposite of that, it's how wide it is. So because, so it's A. Yeah. Now, when it says what is the mean of curve A, isn't the mean right there? So that would be 10. And for this one, wouldn't it be right there? And that would be 4. So these early questions are really just, hopefully, pretty straightforward, right? Nothing too special going on. Now, suppose you were going to sketch a normal curve that had a mean of 15 and a standard deviation of 2. What would it look like? Well, you got a picture of 4, right? Well, the mean is 15. Shouldn't the middle of the hill be at 15? So that one works. That one's no good. That one's no good. That one would work. Now, since the standard deviation is 2, once you got the middle guy, right, 15, shouldn't you then go 17, 19, 21? Do you see it's that one? So if you tell me the mean and standard deviation, I can actually draw a pretty good picture of what that distribution would look like if you drew a sketch of it. So I'm going to do one myself here. That way I might show you how you create it. Suppose you tell me that the mean is 20. Nah, I've done 20, it's picking a number. Suppose you tell me the mean is 12 and that the standard deviation is 2. It would look like this. Right in the center is the mean. Standard deviation is 2. You would go 1, 2, 3 guys. Take away 2, take away 2, take away 2. See how easy it is to draw roughly what all the people in the population would look like, right? That's the kind of histogram that you would see. You can see it's centered on 12 and going up in 2s and going back in 2s. And you notice that you stop at 3. Right? So 12, 14, 16, 18, 12, 10, 8, and 6. For instance, if you only told me that, I could draw this picture. But I could also tell you this. Is 20 an outlier? Is 20 an outlier? Well, look at this data. Would 20 be considered? Yes. In fact, anything that goes beyond these two numbers, right? 3 standard deviations either side is an outlier. Now, the next guy, I'm going to have to show you the picture because there's just too much detail for me to draw it by hand, and I'd probably make it a pig's dinner if I did. Right, are you looking, why is that not? There we go. Are you looking at this guy, number 4? Right. That picture I showed you, right? 1, 2, 3 standard deviations, right? So there's the mean, 1, 2, 3 standard deviations, 1, 2, 3 standard deviations. We even know more than just, 3 standard deviations either side, and that's almost everybody. We actually know even more than that. So here's a very interesting fact. If you take the mean, whatever that is, and you go 1 standard deviation either side, 34% of all the data will be here, 34% of all the people would be here. So together, can you see that middle chunk is 68%? So if I know the mean is 50 and the standard deviation is 2, and I know it's symmetric, right? It's normal in shape. Can't I say that 68% of the people are between the mean plus or minus 1 standard deviations? 68%. Now, if you move outwards to 2 standard deviations, you add another 13.5 here and here, but altogether, do you see that's 95% of all the people in a population tend to be within 2 standard deviations of the mean. That's pretty impressive. Now, if you go 1 more standard deviation out, you add an extra 2.35 either side, and from there to there, so from the mean, 3 standard deviations either side, 99.7% of all the people are in that range. Can you see why, if you're outside that range, you're an outlier? Because aren't you in 0.3%? Isn't that almost nobody's in that kind of place? Right. And that allows us to answer all sorts of questions to do with, well, I'll need to get the numbers on this one, right? So in this story, the mean is 70 and the standard deviation is 2.8. So I'm going to redraw that same picture, but I'm going to put numbers along the x-axis instead of all these sigmas. So that's going to take me just a little bit of time, and then we can look at the questions again. Right. So if you bear with me, it's going to take just a little bit of time. So normal distribution looks like that. Right in the center, we have 70 because they tell me it is. And the standard deviation is 2.8. So 72.8, add another 2.8 is 75.6, and add one more 2.8, and that's 77, 78.4. Now, if you take 2.8 away from this, you get 67.2. If you take another 2.8 away, I'll do that on the calculator, 67.2, take away another 2.8, you get 64.4. And if you do one more, you get 61.6. So there we go. For instance, between here and here, isn't that 1 standard deviation? That is 68% of all the data is in that range. Now, if you go from here to here, right, so that's 2 standard deviations either side, you get 95% of all the people in that range. And lastly, if you go to 3, which is here and here, you get 99.7%. This rule has 2 names. This property, this rule, it's either called the empirical rule, which I don't like, or it's called the 68, 95, 99.7 rule. Now, I like that name because doesn't that name tell you the numbers to use? I don't like this name because I then have to remember these numbers anyway. So why don't I just remember these numbers and have that as the name at the same time, right? So if I asked you, for instance, I better put in all the other bits and pieces. That's 34, that's 34. This little piece in here is 13.5. So is this little piece. This little piece in here is, color them up to that one, is 2.35, and this little piece here is 2.35. Now, if I asked you, for instance, what percentage of people are taller than 70? So what percentage people are taller than 70? Right, if you look at this, there's 70. Taller than 70 is everybody, including that little piece that I don't have a number for, isn't it? Everybody over here. Now, I don't need to add up numbers. Would you agree that's 50%? Right? Aren't half the people going to be taller than 70 and half the people are going to be shorter than 70, right? So the answer to that one would be 50%. Now, if, the next question, what percentage are shorter than that one? Next one is what percentage are between 67.2 and 72.8? Well, if you look at this picture, 67.2 and 72.8, isn't that the 68% of the people, right? From there to there, right? So what percentage of people have a height between that number and that number? One standard deviation. The answer is 68%. Then they finish with, what percentage of people are between 64.4 and 75.6? Okay, what percentage of people using this diagram are between 64.4 and 75.6?
95%.
95%. Now, I wish they had done this question, so I'm going to pretend they did. What percentage are between 67.2 and 75.6? So you notice I've changed that start number to be 67.2. So if you look at my diagram, there's 67.2, right? Starts there and it finishes here. So if I cover this guy up and I cover this guy up, does it help you see what you're going to do to get your answer? Won't you just add up the three pieces of the pie? Right, 34, 34, and 13.5, 68, 78, 81.5, I make that. So using the empirical rule, if you tell me the mean and standard deviation, I can create one of these pictures, and with a little bit of time, can't I fill in all the pieces? And then I can answer questions like, what percentage of people are bigger than this, less than that between these two numbers? And that's essentially what question 4 is about. And then they move on to question 5, which is just like it. The only difference in question 5 is that the mean is 28. Well, there is an extra bit, so I should really do this. So in question 5, the mean, that's what mu is 28 days, and sigma is 2. And this story is talking about the incubation time for chickens. So evidently, if your chicken lays an egg, on average, it's 28 days for it to, well, I guess, break open and become a chicken, whatever. And the difference between this one is that there's 1,000 eggs being incubated. So they're probably putting one of those light places, you know, where you just have a heat lamp and you don't need the chicken to do its thing. Right, so mean is 28, sigma is 2, and they asked us, not typical question is what percentage is between 24 and 32, which would be the typical question. They just ask how many, essentially, out of that would you get between 24 and 32. So there's the mean, right? 28, 30, 32, 28, 24. If you look at the 24 and 32, would you agree that's 2 standard deviations either side? And we know that 2 standard deviations, we use this guy over here, isn't it 95% of the data? So if the question had been what percentage of chickens would hatch between 24 and 32 days, you would have said 95%. But if they had asked you, how many chickens would that be, right? How many out of the 1,000 eggs? Wouldn't you just find 95% of 1,000, which is just 950. So you just do an extra step, right? Instead of saying the answer is 95%, you find what 95% of 1,000 is, or maybe 95% of 200, right? You can imagine the story was 200 eggs, right? Or 2 million eggs. It would be 95% of that number that you would use for you. And that's what that one looks like. Okay, let me just show you the next question. It's quicker than writing it down. Still in the same, 68, 95, 99.7, just the way it's written. Okay, what percentage of the data should be to the left of mu? What percentage of the data should be to the left of the mean?
50%.
50%. Now, what percentage of the data should be between the mean take away a standard deviation and the mean add 1 standard deviation?
68.
68. And if it had said 2, wouldn't we say 95? And now it's finishing with 3. And what's that one? Can you remember the decimal for 3 standard deviations?
99.7.
Right. So if you called the rule the 68, 95, 99.7 rule, won't it make answering those questions a little bit easier to remember? Right. That one's pretty much the same question. Okay, here we go. Probably, yeah, I think I'm going to have to do this one on paper because it's kind of visual. So I'll jump back to doing the whiteboard if this thing wants to. No, darn it in space. Having issues with my windows here. Come on, come back. Okay, we're ready. So in question 8, or at least a version of question 8, at the Burnt Mesa Pueblo, archaeological studies have used a method of tree ring dating in an effort to determine when prehistoric people lived in that pueblo. So basically you take wood and you can look at the patterns in the tree rings and compare them, and you can come up with, each ring is a year, right? So you can compare them with other trees. You do that in Britain a lot, actually. Anyway, back to the story. And the mean in this was 1235 years, and the standard deviation was 32 years. And they turn the story kind of on its head. They want to know what range would you expect in your data to have 68% of it. Well, isn't 68% 1 standard deviation away from the mean? So if you take this guy and you add 32, you'll get 1267. And if you take this guy and subtract 32, you get 1203. So the range that they're talking about is that 68% of the data will be between 1200 and 1267 years old. Right. Which is pretty good estimate, right? So that Pueblo was definitely being used in that range. And the reason why you don't get a fixed number as well, I'm assuming that there's wood, but it doesn't wood rot, so they stick in a new tree when the thing's not working. And so if you're there for hundreds of years, won't there be different pieces of wood being used at different times? And so there's going to be some variation. But you can be pretty sure that that Pueblo was being used in, what, about 1200 years ago for sure, right? 68% of the tree ring data says that's how old the trees were that were being used, that they at least tested. And then they did a 95, which would simply be, well, if you wanted to do a 95%, wouldn't you just take the mean and add and subtract 2 standard deviations? So you would do 1235, add or subtract 2 lots of 32. So it would be that guy, add or subtract 64. So can you imagine taking away and get this answer and adding it and getting the answer? And that would be your one. And the third one, well, that's part B. Third one's a little vague. What range would you get almost all the data? Couldn't they have phrased that as 99.7 instead? And so what you're really going to do is calculate 3 standard deviations, right? And that will give you your range. So I've left a lot out, but that's essentially what you're doing. And question 9 is basically very similar. And that is the end of our first piece of what you need to get from today. So, put a quick summary. If I gave you, oops, one of these guys, would you feel comfortable if I told you the mean and standard deviation, you could draw a picture that looks like this? If I said to you what percentage was between, say, 16 and 24, would you be comfortable in saying, yep, 68%? Or 2 standard deviations, 95%. That's essentially, that's those two done. Now we're on to something a little bit different. It's called the standard score. I prefer its longer name, the standard Z-score, but it's also called the standard score. And let's show you why we need it. I want you to imagine that we have 2 different scores from 2 different people, but we want to compare them fairly. So, John, made up, is my twin brother, and John took a math exam, right? And he got, this is his score, he got 82. And me, I was in a different math class and I got 80. And my twin brother, John, is laughing at me because he was like that. Not that I have a twin brother. And he said, haha, I did better than you. Now, based on this one piece of information, I guess you could argue that quite well. Couldn't you say 82 was better than 80? But you got to remember the background. He was in a different math class when he got his test. So after a little bit of discovery, we found out that the mean of people in his class was 75 and the standard deviation of everybody was 5. And in my class, the mean was 70 and the standard deviation was 3. And now I'm going to argue that I did better than my brother John. And I'm going to say, how did you do better? Well, In our class, it was a harder test, right? The average in our class was 70. You got the easy test, right? In your class, the average was 75. Your class had a lot more variation in it, right? So there was a lot of big scores and some small scores. I had a lot less variation. It's much harder for me to get 80 in this class than it is for you to get 82 in that class. And that's essentially what the standard Z-score allows us to do. It allows us to compare two different data sets which have different means and standard deviations, and to fairly compare them, right? And so we get this guy called the Z-score, or the standardized Z-score. I like just calling it Z-score. And it's calculated using this formula. The data, take away the mean, divided by the standard deviation. It's normally written down using a much more kind of mathematical one, right? X is the data, the score, if you prefer. Mu is the mean, and sigma is the standard deviation. So what we're going to do is we're going to calculate the Z-score for John and the Z-score for Donald. And the person who got the biggest Z-score did better than the other one. You see, that's a kind of a fairer way of comparing two things. Right? Can you imagine you're at a university taking an English class and your friend's taking an English class, but your friend is taking an English class where the professor virtually guarantees that you pass, right? It's pretty lenient. Yeah. I don't worry about the spelling. Did it mean, was it interesting? You know, kind of vague things that you can't really put numbers on. And then you've got the other poor guy. He was getting an English professor who never gives A's. And the reason he says, I never give A's, is because A's means it's perfect. And nothing is perfect. So you can't get an A. Imagine, I'm being extreme here. Can you imagine then that if you looked at the scores, couldn't it be that you got a lower score than your friend, but you actually did better because in his class, getting an 80 was a lot easier than someone else's class, right? So that's what the standardized score does. So let's see what these two look like. I predict that I did better than my brother, but maybe I'm wrong. The Z-score for John would be his score, take away the mean, divided by the standard deviation. And when you're doing this in a calculator, there's a very common mistake that people do. They forget to put brackets in. So bracket, 82, take away 75, close brackets, divided by 5. And that was 1.4. Now, if I didn't put the brackets round and I just wrote it down like that, I mean, doesn't that look almost the same calculation? Look at the answer. I mean, that's ridiculous. Z-scores typically are between -3 and 3. And that 3 is not magic, because the Z-score measures how many standard deviations away from the mean are you. And remember, 1, 2, 3 is almost everybody. So that's why you would get a Z-score. That Z-score there would only happen. That's the kind of the Z-score of getting hit by lightning 10 times. I mean, it just doesn't happen, right? A Z-score bigger than 3 is very rare. Can you imagine a Z-score that's 20 times bigger? Right. Now, let's see if I was correct. This is Donald. And this is me. And my Z-score, well, I got 80, but I'm working on a mean of 70. And I'm dividing that by 3, and I get a 3.3. I did do better than him. In fact, not only did I do better than him, isn't my score exceptionally large? Because any Z-score bigger than 3 is an outlier. So I probably was first in the class. Right. John did okay, right? I'm not saying 1.4 is bad, but would you agree John didn't do anywhere near as good as Donald? And that's the idea of Z-score. It allows you to compare two sets of data, right? And decide between them which one is better. So in the next bunch of questions, you're going to get just some practice at calculating Z-scores. So I'm just going to randomly pick a question. The mean is 24 in this question. The standard deviation is 5. And we're being asked to get a Z-score for somebody who got 19. Well, the Z-score for that person is X, take away the mean, divided by the standard deviation. So it's 19, take away 24, divided by 5. And that ends up being -1. Now, if you wanted to imagine visually, what does that look like? There's 24. A Z-score of -1 means you are one standard deviation away from the mean, but on the small side. So if you look at that guy, there you go. That is exactly what you'd expect, isn't it? 19 would give you a Z-score of -1. Suppose you get a Z-score of 0, because that could happen. What does that tell you about the person's X value if their Z-score is 0? What do you know about the person if their Z-score is 0? Try to phrase it in different ways.
Doesn't it mean that they were exactly average?
Yes, they got 24. Let's pretend this is a test, right? Z-scores of 0 mean you got the mean, right? Whatever the mean is, that's what you got as your score, right? Mr. Average, right? You couldn't get any more average than that guy, right? Bang in the middle. Now, in the next question, they are doing a comparison. So they got a guy called Raoul, and he got a score of 74. And the mean of his history exam, it was a history exam, was 70. And the standard deviation was 3. And that was in his history. And in his biology class, he got a score of 70, but the mean in the biology class was 70. And my apologies, he got 76, and the mean was 70, and the standard deviation was, say, 2. So we're being asked, did he do better in history? Did he do better in biology? Or were they the same? So all we need to do is calculate the Z-scores, right? Bigger Z-score, you did better, right? If both Z-scores are the same, then you did about the same. So let's look at what the history would be. The Z-score for his history would be what he got, take away the mean, divided by the standard deviation. He got 74, take away 70, divided by 3, which I believe is 1.33. And then if you look at the biology, the Z-score, same formula, but with slightly different numbers. 76, take away 70, divided by 2. I think there's a clear winner. Didn't he do better in biology? Now, Z-scores don't necessarily mean the biggest score wins. In this case, it did, right? Remember the one I did where I went and beat my brother, even though my score was lower than his. So z-scores don't care what these are. They don't care what these are or what these are individually. Isn't it when you put the three of them together, it's how they interact to give you a z-score that tells you the truth, right? So you could have a z-score bigger than another one, even although this number's smaller, even although this number's bigger, even although this number is smaller, right? Isn't it the combination of all three that decide the final result?
How would you do it if the score and the class mean were the same?
Also, well, in this case, they were both the same.
Well, like
Oh,
so,
you mean
like
this? Oh, this was the same?
like he received like a 70 on his test, and then the class mean was also a 70. So
Oh, his z-score would be
70,
zero.
70 minus 70, basically.
Yeah, that would get you zero as a z-score.
And so it would just be 0. Would
Yeah,
be your,
and so
okay.
if one of them is 0 and the other was 3, 3 would win, right? And if this was 1.33 and that one was a 0, then this one would win.
Okay.
Right. Which would be the biggest or the best score between a 1.7 and a 2.3? Well, isn't 2.3 bigger? That's pretty obvious. Now, it gets a little bit harder when you have negatives. Both of you did really badly, right? Because isn't a z-score negative mean you got less than the mean, right? So if you got this z-score and I got this z-score, we both weren't doing good in that test. But relatively speaking, isn't negative 1.5 bigger than negative 2.3? So yeah, we both suck, but I suck less than you, right? So when you're comparing positive numbers, it's a lot easier, isn't it, to tell which ones are bigger. You have to think a little bit more when it's negative numbers. Now, in the next one, we are going to look at a whole load of people in a class, and all you're going to see is their z-scores. So for instance, Robert's z-score is 1.22. Linda got 1.74. There's Joel and various other people. Now, which one of these students scored above the mean? In other words, they did better than the average. Well, if you did better than the average, isn't your z-score going to be positive? Right? So Robert, 1, and Linda. Why am I not picking Joe? And it's maybe nitpicky, but I'm not picking him.
Because it's not above the mean, it's the mean.
It is the mean, right? I mean, it's nitpicky, but you know, you got to, that makes sense. We agree. You don't pick that person. Now, when it says which of these scored the mean, it's only Joel, right? And I'm sure, yep. Which ones scored below the mean? Well, wouldn't you go and you'd say Haley and Jan? So Haley and Jan. Now I can actually ask some other questions that they didn't, and I wish they had. Out of all 6 people there, who's the best? Which
Linda?
one of those 6? Linda. Doesn't she have the highest z-score out of the list? And big z-scores mean you've done really well, right? The bigger the better. In that same vein then, which one of these bombed it? Who did horrible?
Haley?
Yeah. Would you agree negative 1.9 is worse than any of the others, right? So they could have thrown those questions, and they didn't, but I think they're good questions to ask, so I did. Now, this question here tells you what the mean is and what the standard deviation is, and they're saying, take these z-scores and turn them back into what the person got, at least to the nearest whole number. So I'm going to have to show you a new formula for that. So here we go, new formula. And here we go. And eventually here we go. Now, the formula that I have already given you is how to calculate the Z-score when you know the score, you know the mean, and you know the standard deviation, right? Now, if you rearrange this formula, you can get the score, and it's going to be the mean plus the Z-score times sigma. That makes sense. If you rearrange this formula, you can now use it to find the score that someone got. So let's take Robert, for instance. Robert had a Z-score of 1.22. They told us in this question that the mean of the class was 152 and that the standard deviation for the class was 17. So I'm now going to get what Robert's score was, and then I'll have to round it off to the nearest whole number because they told me to. So it's going to be 152, the mean, plus the Z-score, 1.22, times sigma. So I can just go to my calculator and do that as a single calculation. 152 plus 1.22 times 17. And the answer I get to the nearest whole number would be 173. Okay, 172.7, 173. So I now know what Robert got in the exam. He got 173. Probably, well, you know, probably an exam at 200, right? And he got 173. We cool? Any questions about that? You feel comfortable about Z-scores? And that you can use them in lots of ways. One of the common ways is to tell who did better than who in a test. Now, we've been dealing with the general normal curve for the most part. Now we're going to look at what is called the, number 4, the standard normal distribution curve. It's also just called the normal distribution, which is a much shorter name. So we're going to look at the normal distribution. Its full title is the standard normal distribution curve. And it's got the familiar shape that you're used to. But I want you to imagine that you got a whole load of data, maybe people's exam scores, right? And I could do a normal distribution, right, where the mean was 82 and 1, 2, 3 standard deviations and all that. But I didn't do that. What we did instead is we took every single person's score and we turned it into a Z-score. And what you get when you do that, right? So if you take any set of data that you want, right, the raw data, right, the IQ 120s, all that stuff, and you turn them all into their Z-scores, right? John got 1.2, Peter got negative 3.2, all that. You get this shape. What Z-score do you get right in the middle? Because this is going to be the Z-scores for the data. What number is that? My finger is pointing at.
0.
0. Now, a Z-score of 1 would be 1 standard deviation away from the mean, a Z-score of 2, and a Z-score of 3. Isn't it really just a very simplified version of sigma, you know, mu plus sigma, 2 sigma, 3 sigmas, right? Isn't it the 1, 2, 3 thing? And yes, it has the same properties. For instance, 68% of all people will have a Z-score between -1 and 1. right? One standard deviation either side of the mean. What percentage of people will have a z-score between -2 and 2?
95.
You know where I'm going with this, don't you, with the next question? But for completeness, let's do it. And if you do 3 standard deviations, won't you have 99.7% of all the data? So if you calculated someone's z-score, 99.7% of them will be between -3 and 3. Can you see the test for an outlier then is a z-score bigger than 3 or a z-score less than -3? Right, that's where the outliers live. So you might get a question that says something like this. Picking John because he's a nice short name. John got a score, an IQ score of 134. And we know that the mean of IQs are 100. And we know that the standard deviation of IQs is 10. So John's z-score would be pretty easy to calculate because I wanted nice numbers, would be 3.4. Isn't John an outlier? If you know anything about an IQ score, based on this scheme then, wouldn't anybody with an IQ bigger than 130 be an outlier? You'd be thinking genius kind of thing on the IQs, if you think IQs are measuring intelligence at least. So there's a usage of it. So the next thing that we're going to do is really twofold. We're going to take an X score, we're going to turn it into a Z score. That we've done before. And then we're going to take it one stage further. We're then going to look at intervals. So for instance, I want to write what does an X less than 30 look like if you turn the data, the X's, into Z scores. So let's suppose that we have a mean of 20 and a standard deviation of 8. And our job is to turn this thing into what would a Z score look like if the data was less than 30. So find the Z score for 30, because that's basically the boundary. The Z score for 30 is going to be X, take away the mean, divided by the standard deviation. It's going to be 30. Take away 20, divided by 8, and that's what, 10, that's 1.25. So there's your answer. So we're still turning things into Z scores, right? But instead of saying, okay, what's the Z score for 30? Aren't we now taking an interval and saying, what would the interval of Zs look like? Right, so if the data is less than 30, won't the Z score be less than 1.25? So any number less than 30 is guaranteed to have a Z score less than this. We go with that? Right, now there are 3 versions of that question. That's the less than one. Suppose I went and said to you, X was bigger than 42. And I want to know what the Z score is. So it's obviously going to follow the same pattern. I'll find the Z score for it. The score, take away the mean, divided by the standard deviation. 42, take away 20, divided by 8. 22 divided by 8 comes out as 2.75. So our answer would be, if you have a score bigger than 42, your Z score is going to be bigger than 2.75. I said there's 3 versions, right? I get a score less than 30, that's the z-score equivalent of that statement. If I get a score bigger than 42, that's the z-score equivalent of that information. The third variation in that looks like this. And let's make that 18. Is a between, right? Couldn't you get a score between two numbers, right? You can have a score bigger than something, you can have a score less than something, and the third one that we're interested in is suppose you get a score between 18 and 23. What kind of Z scores would that be equivalent to? And what essentially, aren't I just going to turn that into a Z score and turn that into a Z score and we're done, right? So you do the 18 one first. The z-score is going to be 18, take away 20, divided by 8, and that's negative 0.25. And if you go to the opposite extreme, which is 23, the z-score is 23, take away the mean, divided by the standard deviation. And I don't know what 3/8 is, so I don't want to risk it. Yeah, that's what I thought it was going to be. 375. So if I gave you the mean and standard deviation, and then I asked you to take an interval like this, or greater than, or a between, do you feel comfortable you could find the z-score equivalent to that same piece of information, right? Because aren't you just turning the ends, whatever the numbers are, into their equivalent z-scores? So far, so good? Any questions? Are we good? Good. Okay. Now they have a question here called question G. If you're wondering what the number is 16. So in question 16G, they say fawn has a weight of 14 kilograms. Would you say it is unusually small? And then they give you one of those 4 sentences. So let's do it by finding our z-score. Now, before I calculate the z-score for this person, I kind of need to know what unusually small should be. Well, if you're small, shouldn't the z-score be negative because you're less than the mean? And if you want to be unusually small, isn't that magic number -3? So if that z-score ends up being anything less than -3, won't that be unusually small? Now, if you take the data and you subtract the mean and you divide it by the standard deviation, I get -0.75. And wouldn't the answer be no? She is small, but not unusually small. So let's pretend I got one that's more like it. Suppose you got 3. Would that work? That wouldn't even work, not with the standard deviation. Oh, let's go the other side. She got 54. Is that unusually large? Right, let's try that one instead. Well, a z-score of 54 would be that. Is that considered an unusually large number?
Very much so.
Right. So in this case, the smaller wouldn't work, right? But in this case, the larger would. So we would say, oh yeah, if you got 54, that's unusually large. So think of that as being, am I an outlier? I think the question makes more sense. Because isn't unusually large an outlier? That's why you're unusually large, or vice versa. Right. And now we're going to do the final part of this section, which is we are going to find areas on a standard normal guy. Now, I could do 1, 2, 3 standard deviations, but we're wanting better than that. Imagine I had a z-score of 1.32, and I would like to know what percentage of the area was 1.32 or less, right? That would be an interesting thing to know. And so we are going to find the area of this. And I can't do the 1, 2, 3 standard deviations because isn't 1.32 not a whole number? It's not 1, it's not 2, it's not 3. And the good news is that all of these questions get done by salt, which means as long as you know how to use salt, they are dead quick, right? So let's show you how you get the answer to this question. Oh, they're all here. Right. What area is to the left of negative 1.44? So I'm going to hit salt button. And it took me, I'm going to have to shrink this up because you can't see everything. Now, can you all see it now? Now, when you go, make sure this thing says normal distribution. It typically should, but make sure it does. Make sure this says 0 and make sure this says 1. If you've got all of those things, you can now find area to the left of a number. You can find area to the right of a number. You can even find the betweens and all sorts of things. So let's suppose I want to know what area is to the left of, what's that question? Let me find that question for a minute. Where are you? Oh, you darn little darling, you haven't done that. Okay. I want to the left of negative 0.45. Okay. Can you still see the picture? Right. Left tail, that's for left. Go down here and make this negative 0.45. Not 10.45. Negative 0.45. You see, you even see a little picture of it. And that guy there is your answer. So the area is 0.3263. I'll write that down. 0.32636. Now I'm going to copy that if it will allow me to. Now I'm going to go here and I'll put the answer in. Now they want it to 4 decimal places, so 3264, I guess. Now that's not the percentage, that is a decimal, but isn't that decimal 32.64%? So if you wanted to know a percentage, 0.3264 is 32.64%. And that's it. So let me go back here. I would like to know what percentage of z-scores are bigger than 2.1. Right-tailed for bigger than 2.1. And the answer is 0.01786. I would like to know the percentage of z-scores between two numbers. So if you hit between and you say, I like to know what percentage of z-scores are between -1 and +1. And the answer we get, maybe I'll make it a little bit bigger. So although you can't see the picture, at least you can see the numbers now. Isn't that darn close to 68%? Remember the 68, 95, 99.7? If you wondered where the 68 came from this guy. Now, if I make it -2 to +2, what number should I get this time? -2 to +2. What percentage? Or is a decimal? What decimal? Okay, I'm going to hit it. Isn't that pretty close to 95%? And for completeness sake, let's do 3. Shouldn't this be done close to 99.7? Would you agree 0.9973 is pretty much 99.7? They use those numbers because they rounded them off. Can you imagine it would be really very weird to say 68.22, 95.03, and 99.73% rule? Would you agree that's overkill? So they just rounded them off to 68, 95, and 99.7, and that works totally fine. So pretty much, if you tell me the Z to start with, or finish with, or bigger than, or less than, won't salt do everything else for me, right? Just make sure that says normal, that says 0, and that says 1, and then choose whichever one of these guys. Left if you want less than, right if you want more than, and between if you want a between. We good? I'm just scanning through. So if you want to the left of 0.71, wouldn't I hit salt and just put 0.71 and get my answer? If you wanted to the right of that number, wouldn't I go right tail and type in that number and get my answer? What's that one to the right again? Another to the right. There's a between, right? So between 0 and 2.94. Do you want me to do another one of the salt ones, or seeing it once enough for you to feel comfortable? You want to see another one? Are we good? Okay, I'm happy with that. And that's us finished then. That's that section. That is finished.
I would note on Salt, I was having trouble opening it on Google Chrome. I also use a Mac, so that could have an issue with it too. But when I downloaded Firefox, it opened just fine.
All right, so your advice then is if it doesn't work with one browser, maybe use Firefox. Right. Me, I'm on a PC. I use Google. It works fine. But
I
there are
always
others.
find little loopholes because a lot of the stuff doesn't work as well on Mac.
So the Mac isn't as friendly as they tell me it is.
Not as friendly.
It's probably Microsoft trying to screw up Mac, you know, or Google trying to screw up Mac. I mean, there's a little bit of professional rivalry, isn't there? They don't want things always to go. You've got, I use Opera sometimes when I have issues. If Google doesn't work, I find Opera works pretty good. I don't know why, but for me. I actually have Firefox, but I don't use it much. But I always have it there, because you know, if you don't have it, there'll be one piece of software or one website that's wonky, and you need to use a different browser. So I do have Firefox as well, but as I say, I don't use it much. So now we're going to move on and show you the next section, because it's got an A and a B to it. And here we go. You ready? Same idea. Let's suppose we have an IQ test where the mean is 100 and the standard deviation is 10. So it would look something like this. And I want to know what percentage of people, or actually what proportion of people, have the following IQ ranges. So my first one is, what proportion of people have an IQ greater than 121? Second question is, what proportion of people have an IQ less than 82? And the third one is, what proportion of people have an IQ between 75 and 105? Right. That's the typical questions that you would want to get from your data, right? So you've collected your data and you know the mean and standard deviation. And what you like to know is what proportion of people are in certain ranges, right? So this is IQ test, right? So an IQ of 121, let's show you how I would do that. And the good news is you kind of already know how to do it. even if you don't think you do. Remember the salt button? I'm going to hit it again. And it's going to be normal. The only difference is if the mean is 100, you put 100 here. And if the standard deviation is 10, you put 10 here. And the first question I wanted to know was what proportion of people have an IQ greater than 121? Right tail for greater. And you make this number 121. And the answer is that guy there, which is what, about 1.8% roughly. So of all the people that you know that's taken an IQ test, only 1.8% of them would have an IQ of 121 or bigger. Now, if I wanted to know less than 82, wouldn't I be picking left tail? I remember things little funny ways. I try little tricks. Left starts with an L. Left is less than. Right, that's the easy way to remember, right? Left is less than, and the others are kind of obvious once you know one. And I want to be less than, what do I want to be less than? 82. And the percentage of people who have an IQ less than 82 is about 3.5% of the 3.6%, or as a proportion 0.03 and 593. And I had as my third one a between, and a between is that one. And I want to be, well, the way the right between is a bit weird, but you have to just live with it. So it's got to be bigger than 75 and less than 105. Now, I think it would have been better for the software just to have, you know, the numbers on either side and the X in the middle. But I mean, you got to live with it, right? It really does have the numbers, doesn't it? You see the numbers. Right, and that ends up being 99.4%. Pretty much everybody is going to have an IQ in that particular range. So are we cool with that? Right. So you can, as long as you know the mean and standard deviation, and your data has that nice symmetric look to it, you can tell pretty much anything you want to know. So pretend I collected data and I know that the average in the test was 55 and that the standard deviation was 5. And I want to know what proportion of the class got greater, so I'll call it X, got greater than 69. And so I've got this thing in front of me. So I'm typing in the mean now, it's changed to 55. I'm changing the standard deviation. I've just changed it to 5. And I want to know bigger than 69. And I can go here and you can't see it, but I'm typing in 69. And the answer that came out was 0.00256. Or if you multiply it by 100, nothing 0.256%. Would you agree that that would be almost nobody in the class? Maybe one person, right? That would be it. Now, there are a number of different ways in which this information is sometimes used. There are SAT scores. Has anybody ever done an SAT score? I'm not going to ask you your score. It's not my job to know that, right? Let's just pretend that the mean of an SAT was 600 and that the standard deviation was 42. And you would get your score, your raw score. So they might tell you that you got 681. And they will also tell you a guy called the percentile. Is that correct? You get told I'm in the 20th percentile or something, or I'm in the 80th percentile. And what is that percentile about? Well, basically what they're finding out is what proportion of people, right, got your score or worse. So again, I've got SALT here, so I'm typing in that the score was 600 and that the guy there was 42. And now I'm putting in what 681 would look like. And that, oops, mishit a number here, 681. And I got, well, as a decimal, I got 0.97 roughly. And that's the 97th percentile. So if you did get that SAT score, and this was the mean and the standard deviation of it, you would be 97th percentile. So can you imagine that this was all the data and this is what you got, because 600 is about here, right? And you got 681. Everybody here, that's 97% of them. Of course, some people like to look at that number, don't you? Because isn't a 97th percentile also you're in the top 3%? So what some colleges can do, at least to get into courses, I'm not sure how much they do it nowadays, but I believe they used to do it. Couldn't they say to you things like you have to be in the 80th percentile or better to get into the engineering program, or whatever percentile they decide on, right? That would be one of the ways in which they could, compare one person to another.
A lot of grad schools use percentiles for entry.
Are they pretty rough depending on the college?
Yeah, up in the high 80s to 90 percentile for entry.
Right. There, I've done not a lot, but I've read a little bit about things like that, and there's some really quite interesting data that I've seen, which basically is a self-fulfilling prophecy. I'll tell you how that works. You know, if you do something because you think it's going to happen, and because you do it, you make it happen. So an example of a self-fulfilling prophecy could be the stock exchange is going to crash, right? The prices are going to go down. Now, if enough people believe that, they will sell their stock and won't the stock market crash and go down. It's a self-fulfilling prophecy, right? Well, having very high percentiles for colleges is very often used as a way of people comparing colleges. And so you say, oh, to get into UW, you need to be in the 90th percentile, but to get into blah, blah, college, it's 18th percentile. And they're looking at different things. But you got to look at it this way. If the only people you pick are really, really clever, right? Because we'll assume that the percentile is a measure of being clever, right? If they're really, really clever, won't they learn regardless of how bad the teaching is at that university? They'll learn themselves, right? They'll teach themselves. They'll figure out how to do it. So won't they have very good pass rates and probably lead to very good jobs because they're already very good students? So if you're looking at what makes a college good or bad, you shouldn't really look at what they pump out. You should look at how good they do with the people they get, right? I mean, if it's kind of mediocre students, but when they pop out the other end, they're actually pretty knowledgeable, that's a good university, right? If they're really clever students and they pop out being really clever, you've probably not done that much, right? They were already really clever, right? They knew a lot of stuff and they figured out the rest themselves.